In the previous video, we talked about electronic structures, and we're going to use some of the same language that we did. So if you haven't watched the electronic structure video, go ahead and watch it. So when I start talking about SPs, Ds, and Fs, and the energy levels, you'll kind of have an idea what I'm talking about. Now, electron configurations are when we take that information from the electronic structure and write it in a way that helps us kind of understand or how we could think about where the electrons are in an atom. And then in the next chapter, we will start thinking how that helps us understand how atoms might want to make compounds with other atoms. So when I talk about an electron configuration, I know on this page I have rules, but I just want to show you what an electron configuration would look like. So for example, carbon, and at this moment, don't worry about how I'm getting it, just look at what it looks like. So the electron configuration for carbon is 1s2, 2s2, 2p2. Now I'm going to show you how to get this, but right now I just wanted you to see this is an electron configuration. It has numbers and letters that represent things in the electronic structure. The numbers that I'm underlining in red right there, those tell us the energy level or the principal energy level. So that tells us the energy level, the numbers I underlined in red. Then the numbers, the letters here, S, S, and P, that tells us the sublevels, and the sublevels. And remember, inside the sublevels, there's orbitals that have the same letters. Right? So that tells us the sublevels, which contain the orbitals. The orbitals aren't separated out in an electron configuration. Remember, an S sublevel has 1 orbital, a P sublevel has 3, a D sublevel has 5 orbitals, and an F has 7 orbitals. So in an electron configuration, they just write the sublevel, but we know that in that sublevel how many orbitals there are. And then the last thing that's on the electron configuration, and remember, I'm going to tell you how to get this. I'm just trying to describe what an electron configuration looks like, are these numbers up here. And these all just happen to be 2s. They won't all be 2s when we write them, but this tells us the number of electrons that are in each level. Okay, so basically an electron configuration is trying to describe where the electrons are in an atom. Okay, so we're going to learn in this video how we can use the periodic table to help us write electron configurations. So before we begin, let's look at some of the rules that we would use to write electron configurations. So here's rule 1, right here. The electrons are placed in the lowest energy level, beginning with 1s. And this is called the Aufbau principle, which just means like building up. So another way to think about it, and these rules I won't ask you just verbatim to write down, okay? But what I want you to understand that the electrons will want to fill whatever's the lowest energy, and then as they move, they'll keep filling up, however many electrons there are, from lowest to highest. And so it's going to fill from lowest energy to highest energy. The second rule here says that each orbital can hold 2 electrons maximum. Now we've already talked about that each orbital holds 2 electrons, so we just have to keep that in mind. Now remember, some sublevels, like the P sublevel, actually have 3 orbitals inside of them. And then the third rule, which I'll demonstrate with something called a box diagram, maybe it will help you see this rule, says that when you place electrons into the orbitals, if the orbitals have equal energy, and you might say, well, what does that mean that they would have equal energy? Right, so the p, or anything like a p orbitals, right? We know that in a p sublevel, there's 3 of them, and they would all have equal energy, all 3 of those. Okay, so what this rule says is when electrons are placed in orbitals with equal energy, the orbitals will half fill before filling completely. So if I draw lines for my orbitals, so let's say these are the p orbitals, and I'll draw a little arrow as an electron. So if I had 3 electrons, they wouldn't go like this. They wouldn't go 1, 2. Okay, no, 1, 2. I said 3 and then I only wrote 2. That's not very helpful. It wouldn't go 1, 2, 3. So it wouldn't do that. That's not, it says it's not going to do that. It says it's going to, if I had 3 of them, what this Hund's rule says is that I would go 1, 2, 3. And if I had a 4th one, then it would come and go. So here, I'll put a 4th one there so they both have 4. So what Hund's rule is saying is they're not going to go 2 in one, then 2 in the next, and 2. They'll go 1, 1, 1, and then they'll pair up. I call it a bus riding rule because I kind of think like when you go somewhere and you don't know anybody, and like let's say you get on a bus and you don't know anybody, your tendency is to get into an empty row seat, right? An empty row. And really, you don't start getting in rows with other people you don't know until all the rows are filled. And the reason maybe we don't do it is we're shy or whatever. Like it takes more energy to get into a row that already has someone in it. Well, the same for electrons. They'll go to an empty one before they pair up, simply because it takes more energy. Now, I want to take this periodic table, and in some of the tutorial videos I have in Blackboard, there are also some, I go over this. So this isn't the only place you can find it, as well as on YouTube. There's lots of really great videos. So this periodic table, we can relate everything in the electron configuration to the periodic table. So you know our energy levels, the 1, 2, 3, our energy levels can be related to the rows. Okay, and for all, so our energy levels are related to the rows. Now, what else do we have? We have energy levels. Okay, then we have the orbitals, S, P, D, and F. So the S orbitals are related to the first 2 groups. Now, on the first row, they're separated from each other, but they're all together. So everything in this purple, these are all in the S sublevel. The P sublevel is related to this block over here. So everything inside the green is in a P sublevel. The D sublevel, whoops, I picked purple again, and it's kind of hard when you have. The D sublevel is everything, these transition elements here in the middle. And then we aren't going to do electron configurations in the F, just based on the class that you're in, but the Fs would all be down here. Now, I do have to say one thing about the how the energy levels relate to the period or row that they're in. When you get down into the D, see what happens in an atom and in this model is that sometimes the energy levels overlap. Because remember, it's not, I use an analogy like it's a building, but there's not a barrier, a physical barrier between each of the energy levels. So in an atom, some things in the 3rd level might overlap with the 4th level. And so what happens is in the D, we find that the level that these are in are actually a level that's 1 less than the row. So all in here, like these would all be 3s, and these would all be 4s. And just bear with me, and we're going to go through an example, and you can see. But the other things over here, like this is the 1st level, the 2nd. If the other ones in the S's and P, the energy level is related to the row. And in the D's, the energy level is related to, it's the row minus 1. Now, if we had to do these down here, it's actually the row minus 2, but we're not going to, I'll put it here just for your clarification, but we're not doing the F. So we won't have an electron configuration with Fs. So this is kind of an outline, and I want to show you, so I did carbon, and I want to show you how we could get carbon. I think of it like reading. Okay, so here is carbon right here. Now, it's like reading, and each box is going to tell me something. So I'm going to always start, like if I was reading a book and I opened the page, I'd always start at the top of the paragraph. So I'm going to start up here. So when I enter in and I start reading, I see that I start in the first energy level, and then I go in, and what I'm in the S's, right? So I know I'm in an S. Now each box is going to represent an electron, and if we look in the S's, there's one orbital, so anything with an S only has 2 electrons. And if you look all the way down, there's just 2 boxes. That represents both electrons. So it would be, I would count 1, 1, 2. So I put 2 electrons in there, and I would stop right here. So 1s2 stops me at helium. In fact, the electron configuration for helium is 1s2. And every element has to go through that first period, so they all start 1s2, you'll see. So now I'm at the end of this row right here, so now I come down to the second one. Well, now I'm in a different level, so I say, okay, I'm in level 2. But when I start in here, I'm still in the S's, so I write an S, and I count 1, 2. Okay, I'm not at carbon yet, so I can't stop. So I come over here, and now I'm still in the second energy level, so I write another 2 because I changed out of the S's, and now I'm in the P's. So I write down a P, and I count 1, 2. And that's how it's like you're reading the periodic table to get the electron configurations. Okay, now I have to erase this. I'm gonna keep using this one. So let me reverse. Well, you kind of think about it. And you can I'm gonna get rid of carbon, and we're gonna try another one. Okay, so let's try another one. Let's go to. We'll just go a little bit further than carbon. Let's go to neon. Okay. So I start at the first level, I say 1. I go in here, I'm in the S's, so I say S, and I count 1, 2. Now I'm down here, so I can't go any further, so I go to the next row. This is 2. 2. I go in the S's, and I count 1, 2. Go across. Now I have a 2, but now I'm in the P's. And I go 1, 2, 3, 4, 5, 6. And that's what I have for neon. Now notice at the beginning 1s2, 2s2, that is how carbon started. It's a pattern, and once you'll see they're all going to start that way. We're just, because we're doing the same thing over and over, we're just stopping at different places. So let me try again. I want to do at least 2 more. And then you can practice, and if you have questions, you can ask me. Okay, so now I want to come down to the third level. Let's go to silicon right here. So I say 1, and then I'm in an S. And I count 1, 2. Then that's the first row, so now I go to the second row, 2. I'm in the S, 1, 2. Go across. 2, and the P's. I count 1, 2, 3, 4, 5, 6. Okay, if you are writing it down as you go, if you're not watching, if I stop there, I'm right here. That would be the electron configuration for a neon. But I don't want neon, so I'm done with that row, so now I got to go to the next row. You can't skip any rows. So that's 3, then 1, 2. Oh, and I'm in an S, sorry. S. The first 2 are always S's. 1, 2. Then I go across. I'm still in 3, but now I'm in the P's, and I go 1, 2, and that's silicon. So see, it's like I'm reading the periodic table. I'm writing down the row, the number I'm in. then what sublevel, S, P, D, or F, and then how many electrons I put in, and I figure out the electrons by counting the boxes. Okay, we're going to do one more, then we're going to talk a little bit more about it on the next page. Some of you, this is what I'll say of all of you. As soon as the light goes off, the light bulb goes off, you'll be like, oh my goodness, I got that. Okay, so let's try one more. Let's try vanadium down here. So, it's a transition metal. We're going to start the same, 1. Then we're in S, and then I count 1, 2. Then I go to the second level, 2. I'm in S, and I count 1, 2. Then I go across, 2, P, and then I count 1, 2, 3, 4, 5, 6. Then I go to the third row, 3. I'm still in the S's when you start, 1, 2. Remember, S's only have one orbital, they always have only 2. Then I'm in the third level, P's. Now P's could have a maximum of 6 because there's 3 orbitals, and you go 1, 2, 3, 4, 5, 6. Oops, I forgot 6. Then I go to 4. This is an S. I count 1, 2. Then I go to 3. Now here, that's the big thing. So when you go into the transition elements, because there's some overlapping, the transition elements, their energy level is always 1 less than the row that you're in. So this is 3, and then now we're in the D's. So we have 3D, and then you just count 1, 2, 3. Okay, so let's look at this a little different. Well, look, I have some electron configurations and show you how we write it up. So here I have nitrogen, which has 7 electrons, and here's its electron configuration, which we've been working on. There's also something called an orbital diagram, and an orbital diagram is really just a picture of the electron configuration. So oh, darn it, sorry. So I'm rewriting nitrogen a little bigger. So an orbital diagram just draws, instead of just putting S's like the sublevels, they write boxes for the orbitals. So S or S's, anytime you're in S, you only have 1 orbital. So 1S would have 1 box. That's how you draw it. Then a 2S, it's also just going to have 1 box, because anything S, no matter what energy level it's in, only has 1 orbital. And then the P's, we know anything with a P has 3 orbitals, so we would have this whole thing right there, those 3 boxes. Whoops, I shouldn't be writing the 3. That's a 2P. Okay, so then this is the beginning of an orbital box diagram. Then inside the orbital box diagram, you use arrows to do the electrons. So right here, on the first level, there's 2 electrons, so you go 1, 2. Now usually they use half arrows or arrows, it doesn't really matter, but 1 arrow has to be up and 1 arrow has to be pointing down. It's because in this model or theory, the 2 electrons, in order for them mathematically not to be the same, they have to have what's called an opposite spin. So when we're drawing electrons, we just make sure 1 goes up and 1 goes down. Now the second level, it also has 2S also has 2 electrons, so that has 1, 2. And then this 2P has 3 electrons, so remember the rule? It would go 1, 2, 3. They go in an empty box first. Now when they are together, you see it's called paired. When they're just a single electron, it's called unpaired. Now, another thing that we label quite often, and this will be important in the next chapter, is something called the valence electrons. Now, valence electrons simply mean they're all the electrons in the highest level. Well, how do we know what level they're in? We look at these numbers. That tells us the level. So in nitrogen, there's some electrons in level 1 and some electrons in level 2. Well, number 2 is higher. So all of these in level 2 are the valence electrons. So we could say 2s2, 2p3, those are the valence electrons. Or if you want to add them up, we have 5 valence electrons. Now here's something really, really cool. If you're in group A, and you can go back in one of the videos on the periodic table, we talk about anything group A or main group elements. So if it has an A, the number of valence electrons is the same as the group number. So I'm going to turn the page backwards. Okay, so we were just doing nitrogen, right? And nitrogen, if you look right there, has the number 5. And if you might have to look on your own periodic table, I know it's kind of small in the video. But it's number 5. Everybody in this group has 5 valence electrons. In the halogens, this has number 7. Everybody in this group has 7. In these, the alkaline earth metals, everybody has 2 because they're in group 2A. Now this would not be true. We don't usually talk too much about valence electrons in the transition elements. It's not the B's. It's only the ones with the A's. So these have 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. And so if the question is just how many valence electrons, if it's in the main group elements, just look at the group number. You don't have to do the whole electron configuration. Now I have titanium here as another example. So you can review titanium. So here's the electron configuration here. And then the orbital diagram, remember, so if it's an S, it only has 1 box. So it's 1s2, 2s2. The P's have 3 boxes. It's 2p6. The S has 1 box, 3s2, see 2 arrows. The P's have 3 orbitals, so it has 3 boxes, and this one has 6, so you'll have them all filled. 4s, it's an S, so it only has 1 box, 2. And then the D's remember have 5 orbitals. So a D has 5 orbitals, so that means 5 boxes. We talked about that in the previous video. So there's 5 boxes, but there's only 2 electrons. So you have 5 boxes, but there's only 1, 2, because you only have 2 electrons to make titanium. So if I had to do a valence electron on this one, remember valence is the highest level, so I have a 1, 2, 2, 3, 3, 4, 3. Those are all my levels. And the highest one, then if I look at those numbers, is a 4. So right there, I would consider that my valence electrons because it's electrons in the highest level. Now, sometimes you will notice, and in this class it's not quite so important, but sometimes you will notice a shortened configuration. And in a shortened configuration, they go to the closest noble gas in front of it, the noble gas in the column, and then they just write what is remaining. So let me see. I'm going to write the electron configuration, and while I'm writing it, you can look on your periodic table and see. What if I wrote the electron configuration for selenium? It's going to be long. So it's 1s2. You can look at you try to write it while I write it. 3s2, 3p6, or pause it. Try. I hope I have enough room. It's 4s2, 3d10, and then 4p4. Sorry, 4p4. It's kind of squishy. Now, if I'm looking at selenium, I'm going to look back on the periodic table. I use this guy a lot. So selenium, I'm sorry, is, let me take an eraser and erase that right there. Selenium is right here. So to do a short notation, you go to the noble gas and the period before it. It has to be a noble gas. So the one in front of selenium is argon. So, So I would write in brackets argon. That basically tells you that up to argon it's full, and that is all of this. And then what you do is all you're going to do is, let me erase this middle part. is write the electrons that are in that row. So I would write all of this as an electron configuration. So that means it would be 4s2, 3d10, 4p4. And so you can see why when you get further down in the periodic table, people like to use shortened notation because it's just a little bit easier, takes up less space, and you're not writing as much. And here, I've mentioned this about valence electrons, but there it is again in words. Remember, these are the outer shell electrons. So a question I always like you to be thinking about is, why are chemical properties similar for elements in the same group? And it has to do with their outermost electrons. Elements in the same group have the same valence electrons. Now also, one thing we do with valence electrons is sometimes we do dot symbols. And dot symbols represent, that's a way to represent valence electrons. So carbon, which is in group 4A, has 4 valence electrons. So we just write the symbol carbon and then write 4 dots around it. Nitrogen is in group 5A, so it would have 5 dots. 1, 2, 3, 4, 5. And then oxygen is in 6A, that's its valence, so it has 6. 1, 2, 3, 4, 5, 6. So electron dot symbols are just kind of a simple way to represent how many valence electrons are in an atom. Okay, so it's time for you to practice, and please let me know if you have any questions.